Welcome to this comprehensive guide on K-nearest neighbors, one of the most intuitive and widely used machine learning algorithms. This is AI Academy, and in the next 15 minutes, we'll explore how KNN works, when to use it, and see it in action with real examples. By the end of this video, you'll have a solid understanding of this fundamental algorithm that every data scientist should know. Here's what we'll cover today. First, we'll understand what KNN actually is and the intuition behind it. Then, we'll dive into how the algorithm works step by step. We'll explore the different types of problems KNN can solve, see practical examples, and discuss the advantages and limitations. Finally, we'll cover some important considerations when implementing KNN in real projects. K-nearest neighbors is a supervised learning algorithm that makes predictions based on the K closest data points in the training set. Think of it this way. If you're trying to decide what type of restaurant to open in a new neighborhood, you'd probably look at what types of restaurants are already successful nearby. KNN works exactly like this. It looks at the nearest neighbors to make predictions. The K in KNN represents the number of neighbors we consider. If K equals 3, we look at the 3 closest data points. If K equals 5, we look at the 5 closest points, and so on. It's called a lazy learning algorithm because it doesn't build a model during training. Instead, it stores all the data and does the computation when you ask for a prediction. The core assumption of KNN is that similar data points are likely to have similar outcomes. This is based on the principle of locality. Things that are close to each other tend to be more alike than things that are far apart. Imagine you're a real estate agent trying to price a house. You'd naturally look at similar houses in the same neighborhood, houses with similar square footage, number of bedrooms, and lot size. KNN does exactly this mathematically. It measures similarity using distance metrics and assumes that if two houses are close in terms of their features, they should have similar prices. Let me walk you through exactly how KNN makes a prediction. Step 1. Calculate distances. When we get a new data point, we calculate the distance between this point and every single point in our training dataset. The most common distance metric is Euclidean distance. Basically the straight line distance between 2 points. Step 2. Find the K nearest neighbors. We sort all these distances and pick the K smallest ones. These are our nearest neighbors. Step 3. Make the prediction. For classification problems, we take a majority vote among these K neighbors. For regression problems, we typically take the average of their values. Let's say we're classifying emails as spam or not spam, and K equals 3. If 2 of the 3 nearest neighbors are spam and 1 is not spam, we predict spam. For regression, if we're predicting house prices and our 3 nearest neighbors have prices of 300K, 320K, and 280K, we'd predict 300K as our answer. The choice of distance metric is crucial in KNN. Euclidean distance is the most common. It's the straight line distance we're familiar with. The formula involves taking the square root of the sum of squared differences between coordinates. Manhattan distance, also called city block distance, measures distance as if you're walking through city blocks. You can only move horizontally or vertically, not diagonally. This can be useful when features represent different types of measurements. Minkowski distance is a generalization that includes both Euclidean and Manhattan as special cases. There's also cosine distance, which measures the angle between vectors rather than their magnitude, and it's particularly useful for text data or when dealing with high-dimensional spaces. Choosing the right value of K is one of the most important decisions in KNN. If K is too small, say K equals 1, our model becomes very sensitive to noise and outliers. One mislabeled data point could completely throw off our predictions. If K is too large, we might include too many distant points that aren't really relevant, making our model too general and potentially losing important local patterns. As a rule of thumb, K should be odd for binary classification to avoid ties. Common approaches include using the square root of the number of training samples or using cross-validation to test different values of k and pick the one that performs best. There's also a bias variance trade-off here. Small k values lead to low bias but high variance. The model is flexible but unstable. Large k values lead to high bias but low variance. The model is stable but might miss important patterns. Let's look at a concrete classification example. Imagine we're building a system to classify fruits based on their weight and sweetness level. We have training data for apples, oranges, and bananas. Now, we get a new fruit with weight 150 grams and sweetness level 7. With k equals 3, we calculate distances to all training points and find the 3 nearest neighbors. Let's say we find 2 apples and 1 orange as the closest neighbors. Since we have 2 votes for apple and 1 vote for orange, we predict this new fruit is an apple. This is the majority vote principle in action. If we had k equals 5 and got 3 apples, 1 orange, and 1 banana, we'd still predict apple, since it has the most votes. For regression, the process is similar, but instead of voting, we average the values. Let's say we're predicting house prices based on square footage and number of bedrooms. We have a new house with 2,000 square feet and 3 bedrooms. Using k equals 3, we find the 3 most similar houses in our training data. Let's say their prices are $350,000, $370,000, and $330,000. For simple KNN regression, we'd take the average, 350 plus 370 plus 330 divided by 3 equals $350,000. That's our prediction. We can also use weighted averages, where closer neighbors have more influence on the prediction. This makes intuitive sense. A house that's very similar should have more say in the prediction than one that's just barely in the top k. KNN has several compelling advantages. First, it's incredibly simple to understand and implement. There's no complex mathematical optimization or parameter tuning during training. It's non-parametric, meaning it doesn't make assumptions about the underlying data distribution. This makes it very flexible and able to capture complex patterns that linear models might miss. KNN works well with numerical and categorical data and can handle multi-class problems naturally. It's also very effective for recommendation systems. Think of how Netflix might recommend movies based on users with similar viewing histories. Perhaps most importantly, KNN can capture local patterns very well. If your data has different behaviors in different regions, KNN can adapt to these local variations automatically. However, KNN also has some significant limitations. The biggest issue is computational cost. Since we need to calculate distances to every training point for each prediction, it can be very slow with large datasets. Storage requirements are also high because we need to keep all training data in memory. This can be prohibitive for big data applications. KNN is sensitive to the curse of dimensionality. As the number of features increases, all points start to look equally distant from each other, making the algorithm less effective. This is particularly problematic in high-dimensional spaces. The algorithm is also sensitive to irrelevant features and outliers. If you have noisy or irrelevant features, they can dominate the distance calculations and hurt performance. Feature scaling is crucial because features with larger scales will dominate the distance calculations. So when should you use KNN? It's particularly good for small to medium-sized datasets where you can afford the computational cost. It works well when you have a good understanding of meaningful distance metrics for your problem. KNN is excellent for recommendation systems, pattern recognition, and cases where local patterns are more important than global ones. It's also great for problems where you need to understand why a prediction was made. You can always look at the nearest neighbors to explain the decision. However, avoid KNN for very large datasets, high-dimensional problems without proper dimensionality reduction, or when you need real-time predictions with strict latency requirements. It's also not ideal when your data has many irrelevant features or when global patterns are more important than local ones. Here are some practical tips for implementing KNN effectively. First, always scale your features. Since KNN relies on distance calculations, features with larger scales will dominate. Use standardization or normalization to put all features on the same scale. Use cross-validation to choose the optimal K value. Don't just guess, test different values and pick the one that gives the best performance on validation data. For large datasets, consider using approximate nearest neighbor algorithms or data structures like KD trees or LSH to speed up the search process. These can dramatically reduce computation time. Handle missing values carefully. You might need to impute them or use specialized distance metrics that can handle missing data. Also, consider dimensionality reduction techniques like PCA if you're working with high-dimensional data. KMN has numerous real-world applications across different industries. In e-commerce, it powers recommendation systems. Amazon uses collaborative filtering based on KNN to suggest products based on similar customers' purchases. In healthcare, it's used for medical diagnosis by finding patients with similar symptoms and medical histories. Financial institutions use it for credit scoring and fraud detection by identifying transactions or customers similar to known cases. In computer vision, KNN helps with image classification and object recognition. It's also widely used in text mining for document classification and sentiment analysis, where documents are compared based on their word frequencies or semantic similarity. Let's summarize the key points about KNN. It's a simple, intuitive algorithm that makes predictions based on the K nearest neighbors. The core idea is that similar inputs should produce similar outputs. The algorithm works by calculating distances, finding the K nearest neighbors, and then either voting for classification or averaging for regression. The choice of K and distance metric are crucial decisions that affect performance. KNN's main strengths are its simplicity, flexibility, and ability to capture local patterns. Its main weaknesses are computational cost and sensitivity to high dimensions and irrelevant features. Remember to always scale your features, use cross-validation to choose K, and consider whether KNN is appropriate for your specific problem size and requirements. When implemented correctly, KNN can be a powerful tool in your machine learning toolkit. Thank you for watching this comprehensive guide to K nearest neighbors. You now have a solid foundation in one of machine learning's most fundamental algorithms. If you found this helpful, please like the video and subscribe for more machine learning content. In the comments, let me know what algorithm you'd like me to cover next. For your next steps, I recommend implementing KNN on a small dataset to see how it works in practice. Try different values of K and distance metrics to get a feel for how they affect performance. Check out the links in the description for additional resources and example code. Thanks again for watching, and I'll see you in the next video.